A reminder that on Wednesday, when we return, there's no class on Monday, your next homework is due. If you've got questions, between now and then, you should be emailing me. We want to continue our examination of discrete probability distributions and the way discrete random variables work. These were the two rules we came up with. To each outcome or value of our random variable, we assign a probability. They don't have to all be equal. Depends on the situation. And then I know that that actual probability must be some number between 0 and 1 inclusive. And the total of all the probabilities have to add up to 1. So how do we create such an item? Well, I can do it in many different ways. But let's start with a theoretical probability distribution function. I have here a presumed fair coin. I want you to flip this 3 times. I want you to count the number of heads you get. So our random variable x is described by our experiment. That's what we're going to do. What are the options available to me for the outcomes of this random variable? What are the outcomes? What are the options for the outcomes of x? That's for one flip. We're flipping 3 times and we're counting the number of heads. What are my possible results? Or no heads. I get 0, 1, 2, or 3. So I know that the set of outcomes looks like this. In order to build a probability density function, I have to come up with what's the chance I get 0 heads, what's the chance I get 1 or 2 or 3 on this coin, assuming that you're right and it's a 50-50 chance heads or tails. I need a sample space. And if I can write out the sample space, then I can figure out the probability of each event by counting the number of favorable outcomes in my sample space. So, how would you figure out all the possible things that could happen when you flip the coin 3 times? Knowing that each flip is heads or tails, how many different options are possible? This is exactly what we did on Wednesday. You flip this coin 3 times. You get a head or a tail each time. You write down a list of what you did. How many possible different results can you get? I'll get 3 results, each one being a head or a tail. I flip the coin the first time. How many options? Flip number 1, 2 options. Flip number 2, flip number 3. I need to flip all 3 times. So I need flip 1 and flip 2 and flip 3. What's the word "and" tell me to do with those numbers? Multiply. So I should have 8 different options in my sample space. So let's write out 8 possible lists. How do I figure out what those 8 lists are? Let's make a tree. Flip number 1 is a branch, right? It either goes heads or tails. Flip number 2 happens after that. And then flip number 3. Notice that there are 8 leaves, 8 ends of my branches here. So if you start all the way on the left and you follow the branches to one of the leaves, you'll get a set of 3 letters, and you'll get 8 different possibilities. And now I have my sample space. I can build my probability distribution, because you can tell me how many of those fit each of my categories. How many of those options up there have no heads in them? Just the one down here. Out of 8, so the probability of no heads is 1/8. How many that have 1? See different hands from different people. How many? Just 1. Exactly 1. I got 3 of them. 1 here, 1 here, 1 here. Out of 8. How many have 2? And only 1 of them. Now look at each of those probabilities. Each individual probability is a number between 0 and 1. And the total of them, add them all up, you get 8 over 8. 1. This is a PDF, a probability distribution function for our random variable, count the heads and 3 flips of coins. Oop, sorry about that. In one sense, this very much looks like a frequency diagram, frequency distribution. Only instead of just counting how many, 1, 3, 3, 1, we've counted out of 8s. That's a huge hint to me that really underlying this probability distribution is a frequency distribution. That means somewhere in here there's a histogram. I could draw a vertical bar of the right height for each of these and make a visual for this probability that would look exactly like the histogram for the corresponding frequency distribution. Who was it that said at least? Is that you? At least? So if I'm looking at the difference between exactly or at least or at most, when we did our frequency distributions, we also did a cumulative frequency, right? Remember that ogive graph, that extra line that added up everything that went before it? So I could do another table that's called a cumulative distribution function. And instead of being P of X, it's the chance of X less than or equal to whatever our value is. And all it does is it adds up. So here, that's still 1/8, but what's the next one? It adds the 2 values. And the next one adds this next value on. And notice by the time we hit the end, we've got them all. We have a 1. This cumulative distribution function behaves slightly differently. I suppose technically I wrote something slightly wrong. Let me go back up there. In this one, instead of writing just P of X, I'm going to write it P of X equals our number. And then we can more clearly see the difference between these two. Equal versus less than or equal to. If I were to make the appropriate histogram for the PDF, all of those heights would be really small. But that's okay. I can just scale up the picture appropriately. And then I would make a vertical bar of the appropriate height for each of these. Zero column, 1 column, 2 column, 3 column. There we go. I could also make a CDF histogram. That would have to go all the way up to 1, right? And it would look like it got bigger over time. Bottom of page 197. Here's a particular PDF. Gee, that looks awfully familiar. What does that look like? I've seen a picture that looks like this before. That normal distribution. And then this kind of resembles that ogive that comes out of it. The height of all of these would have been that red line that was drawn across the histogram. PDF, CDF. They've done the entire y-axis in decimals. I don't care. But with a PDF, I can answer questions about my random variable. Of capital X equals a little value x. 0.5, no, 0.05, 0.3, 0.25, 0.2, 0.15, and 0.05. So here is a PDF. On the midnight shift, the number of patients with head trauma in an emergency room is found to obey this probability distribution. Problem 6.3, page 198. What is the chance that you will get more than or equal to 3 head trauma patients in a night? Bigger than or equal to 3, 3 or more. Say again? How do you get that? But I'm not adding what goes up to 3. I'm adding what's beyond 3. Right, 3 or more. X bigger than or equal to 3. So that's the chance of 3, the chance of 4, the chance of 5. So there's a 40% chance. What's the chance it's 2 or fewer? How did you get that number?
Well, first way I did it was
You could take the 0, the 1, or the 2 and add them up, right? But you know it's either 2 or less, or it's not 2 or less. Not 2 or less is 3 or more. There's a set term, there's a probability term, that's a complement, right? And we said the chance of something's happening is 1 minus the chance of it not happening. Now that's actually a pretty useful statement because sometimes there are a lot of options in the thing I'm trying to count. Adding them all up would be a pain in the neck, but there are only a few that don't happen. So let's count those and take them away from 1. Since this is discrete, there's no option between 2 and 3. I mean, these are people. You don't have 2.5 people show up in the ER. At least I hope not. That's not a good thing. So if I'm looking at the difference between less than 4, less than or equal to 3, those are the same, aren't they? Because there's nothing under 4 between 3 and 4. But that's actually the next question in the textbook. It says, what's the chance of being less than 4? But you've already answered that. Because the stuff that's less than 4 is the same as less than or equal to 3. I can go back up and count. That was actually the 0.8 you gave me earlier. Out of these two calculations could have been done with a CDF because we're asking about less than or equal to. But that first calculation could not have been done with a CDF except by exploiting what you did and saying, oh, if I want bigger than 3, I need to know what's the opposite of that will be less than. And less than is what shows up on a CDF. Questions? Most random variables are described by a few parameters. Rather than actually giving me a chart with a probability distribution, they give me some formulas that are related to that. And those are based on some parameters and characteristics. And once I know what those associated characteristics are and what the parameters are in my population, I can then say, oh, this sort of a formula, this sort of a chart, this sort of an idea will be the most helpful for a particular PDF or CDF. In a more general statistics class, there are usually 7 particular formulas we use a lot. We're going to limit that number substantially. But what are some of the parameters I might use to describe a random variable? The two most common are expected value and variance. Variance. I've heard that term before. Where have we heard variance before? I guarantee you it showed up in your notes before. It wasn't in the last chapter. It should have been in the one before.
have something to do with standard deviation?
It absolutely does have something to do with standard deviation. And that's exactly where we're going to use it here. Expected value then is the same idea as a mean, an average, and a variance goes with a standard deviation. We're looking at the same ideas as we did in chapter 4. We're just going to apply them to these now. All right, in order to do variance, standard deviation, I need an average. The probability version is called an expected value. E of x. Because x is our random variable, right? So E of x is the expected thing from x. And it measures the center, just like an average did. As a matter of fact, an expected value is a type of mean. Okay, wait a minute. We used the symbol mu for a mean, right? I'm going to use that same symbol in addition to E of x. How do you get an average? You add up what's there and divide by the total, right? You add up what's there and you divide by the total. Wait a minute. I'm dealing with a probability. What's the total of all of my probabilities? 1. I don't have to divide by it. It's already incorporated into this setup. Now, what the hell does this say? What this says is you take each value of your random variable and multiply by the corresponding probability. Let's go back to our coin flip as an example. But that capital, this one, that's the capital letter sigma. It means sum. Normally, there's an indicator that we're doing whatever I values go in it. So I goes from 1 to however many you got. You'll often see it written like this.
It's like the repeated.
Yeah, just repeatedly add. Yeah, capital S in Greek. So, for our coin flip, we had a table that looks like this. We had the values from 0 to 3 at the top, with the chance of each one occurring at the bottom. Gesundheit. All I want you to do is multiply down the columns and add up the result you get. Now, please note, this is where it is possible for you to tell me that the average number of kids in a family is 2.3, right? I don't know how to have 0.3 of a kid, but there are more with 2 than there are with 3. What's the average here might not be the number 0 or 1 or 2. It might be something in the middle. And based on our histogram, where do you think the center is going to be? Oh, yeah, right there in the middle between 1 and 2. What do you get for your number when you do this? Take each value and I multiply it by the corresponding probability. That first number is 0, then 3 over 8, 6 over 8, and another 3 over 8, 12 over 8, which is 1.5. Right in the middle between 1 and 2. Now again, I don't know how to flip a coin and say on average, I expect 1.5 heads. Coin's going to be balanced on edge, hanging in midair. No, I mean, some people will get 2, some people will get 1, some people will get 0, some people get 3. But if you average all the results, the average should be 1.5. What about our patients with head trauma idea? This distribution. What is the average number of patients with head trauma in the ER if this is the distribution? I'm going to copy down the table again so we have it, but you should already have it in your notes. Do I hear other people agreeing with 2.25? I get at least one more head nod. Some of you are still working. I'll give it another minute. I happen to agree with you. Now, again, I hope you're not getting fractions of people in the ER. But that means if I look at this over several nights, over a month, over a year, on average, 2.25 people a night. So more likely 2 than 3, but there are some 2, some 3 nights, there are some 5 nights. There are just fewer of them. Questions? Where am I going to use this? Who drives? You got insurance, right? How much? You total your car. Chance you totaling your car. I hope. I hope the chance of you totaling your car is really small. But that's why you have insurance, right? Let's suppose that the chance you get into an accident that totals your car is 1%. If you total your car, your insurance company pays you. Depending on the amount of your policy, they pay you a certain amount. I'm going to assume you have really good insurance and you pay whatever it is you pay. They pay you $50,000 for your car. So let's let our random variable be the amount paid by the insurance company. And we just said that the chance of you totaling your car, which would cause them to pay $50,000, the chance is 1%. And that means that 99% of the time, they don't pay a dime. Now, I know most insurance policies have multiple levels in here, accidents, other coverages, etc. You ding up a door, bang a fender, something like that, maybe they pay something in the middle. I'm just going with catastrophic coverage and nothing else. What does the insurance company expect to spend on you? On average, I'll need the expected value of this policy. What is the expected value of this insurance policy? Oh, the expected value of this insurance policy is 0.01 times 50,000 plus 0.99 times 0. Most of the time they spend nothing on you, but there's that 1% chance they're going to have to pay you $50,000, isn't there? And if you do this multiplication, what does that turn out to? Which means the insurance company should expect that you will cost them $500. Therefore, your payment better be at least $501. If they've got 100 different drivers that they're insuring, and they charge each and every one of you $500, then when that 1% has an accident, they have $50,000 sitting there to give that person because they've charged each of you $500. This is how insurance companies decide on rate setting. They say, what's the chance I'm going to have to pay out this much to all these different people? How much do I need to bring in? So I don't have the money out of my pocket, and I have to cover my overhead. All of a sudden, I have a way to set a rate. Now, the more options you put into play here, the more complicated this distribution looks like, the more options you have for coverage, right? I didn't say anything about what you get for getting hurt in this. What's your hospital coverage in this? Personal injury and property. You didn't hit another car, you hit the side of the house. There's all sorts of other things that go into an insurance policy like this. So somewhere, some probability guy is sitting in a room figuring out how likely it is that you're going to have an accident based on your age, gender, driving environment, the age of your car, and all sorts of other options. And that person is called an actuary. And they make bank. All they do is this sort of statistics. They do it for insurance, for car insurance, medical insurance. The first actuary I ever met worked for the Florida Farm Bureau. He forecast weather conditions and orange juice prices. Any of you see the Eddie Murphy movie, Trading Places? Eddie Murphy, Dan Aykroyd, this is a movie from the 80s. Go watch this movie from a business perspective. It's effing hilarious. They corner the frozen orange juice market by faking a report. The Florida actuary I met wrote that report in real life. In 1987, he was making $250,000 a year. It's just statistics. Why the hell do I need this? By the way, this same expected value, this same average, in physics, is a balance point. Just have your bats with you. No? Okay. Baseball players, I can grab a bat, pick up a rod of any type, a cane, a baseball bat, put one finger at each end. Now bring them together slowly. And don't let it tip, don't let it fall. Your hands will come together at some point. That point is the average of the weight balancing the thicker end versus the thinner end. That's the sweet spot in your bats, guys. It's an expected value. Useless. You're never going to see it anywhere. Variance. If I've got a mean, I have a standard deviation. I have a variance. Now, I got to go back and think of what we did when we did standard deviation, we did a bunch of extra subtractions and the average was in there. So what I need to do is I need to take each probability and I need to multiply by the difference between that item and the average squared. And then I add all of those up. And that's my variance. But because there's a square in there, we're going to call this S squared. We're calling it in Greek. So that's a sigma. That was the symbol we used for the standard deviation, wasn't it? Just sigma. So if I take the square root of this, I get a standard deviation. So really, you could use the variance or you could use the standard deviation. They both tell me the same thing, but what is it they tell me? They tell me the width of my distribution. They tell me how wide it stretches from that center. If my standard deviation is small, I expect everything to be nice and close around the average. If my standard deviation is bigger, I expect it to be wider and fatter and thus spread out more. So if I go back and I look at that normal distribution PDF on page 197, there's something in here about the standard deviation, but if the standard deviation was bigger, I'd expect the lower peak and wider tails. And if the standard deviation was smaller, I'd expect lower tails and a sharper, higher peak. More on the precise imagery to come. But I could do this calculation by hand. I rarely will. 99% of the time, if I'm doing this, I'm going to throw all these calculations into Excel and let it chug it out. But we had a small distribution, right? Our dice, coins. And we already worked it out that the average, the expected value, was 1.5. So if I want the standard deviation for this particular setup, I'm going to build this. So for each number, because these are my xi's and these are the probabilities, I'm going to subtract the average. So 0 minus 1.5 squared times the probability, 1/8, plus 1 minus 1.5 squared times 3/8, and so on. 2 minus 2.5 squared, sorry, about 1.5 squared times 3/8. And then last, 3 minus 1.5 squared times 1/8. This is my variance. Grab your calculators. Let's go to town. I'm converting all of my fractions to decimals. So 1/8 is 0.125. 3/8 is 0.375. A little bit of calculator work later. What do you get? Yes, that's this first number, 28125, and then 0.09375 twice, because those are the same. And then this number is the same as that one. So I get another 0.28125. And when I add them all up, and that is the variance. That is sigma squared. Lowercase s, not capital S. So really, if I want the standard deviation, what do I do with this number? I take the square root. 0.866. That's my standard deviation. Hey, wait a minute. The histogram we drew for this picture that's got that sort of normal shape to it, doesn't it? So maybe the standard deviation and the mean relate to how this looks as a normal. But there are other kinds of distributions. I will get more specific examples on Wednesday. Please note, there are a bunch of very good examples and sample problems here. Here's one about contest, giving away a Lamborghini. What's the chance you're going to win a Lamborghini? What's your expected value there? Insurance policies for dormitories. Useless crap. I'm never going to need that. Renters policies, people. There's all sorts of stuff in here. Lottery winnings. They're all based on expected value and standard deviations. I will see you all on Wednesday. Please remember your homework is due. Have a wonderful weekend.